Hello and welcome to another video. In this one we're going to be going over a number of wonderful substrings. And in this one, a string is a wonderful string if at most one letter appears an odd number of times. And so they give you some examples. So let's take a look at some of these. So in like ABA, A works, B or ABA because at most one character appears an odd number of times. So in the second one, they have all these. And then here there's H and E. And so the word is 10 to the 5th, and you only have 10 characters. So let's take a look at an easier example of this. So let's just say I want to know how many strings are in here where A appears an even number of times. So A appears even. And so this is very similar to, I think there's some problems called like subarray sum equals k and things like that. You can't really do a sliding window because some like huge strings are valid, like this whole thing is valid, but then like some small strings are invalid, right? So like AB is invalid, so that wouldn't really work. But you can basically do like a count. So in here, oh, I don't need this. So basically if you start here, we can just keep track of like how many times we've seen A odd or even in a hash map. And then anytime, so let's say like A is like even, like the count of A is even here. In any other place where A is even, like let's say A is also even here. That means that this middle part has to be even, right? Because like if there's like 2 A's here and 4 A's here, the subarray between those has to be even. Similarly, if these are both odd, right? If there's like 1A here and 3 A's here, then the middle is even as well. So essentially, if both are even or if both are odd, that means I can make a subarray. And so we can just record how many times we've seen even, how many times we've seen odd, and then wherever we're at, we can just say like, okay, if this is even, then the number of times we've seen even before is how many subarrays we can make. And so I'll kind of walk through how that's going to work. So yeah, so let's get rid of this. And let's start here. And for these kinds of problems, you always want to mark 0 to 1 because like the empty subarray is even. That way, like if we have an even number of A's here, that means that for the whole array, the number of A's is even. So you want to always mark this as this. So now let's walk through this thing. So in the beginning, we get to 0 is A. So we check, okay, so here A is not, here we have 1A, right? So we have 1A. So have we seen an odd number of A's before? No, we have not. That means we don't have any even subarrays. Then we keep going. Here we still have 1A. Now here we have 2 A's. But really, we don't really need to record the number. We can just flip the number. So we can just flip it from 1 to 0, because all we care about is odd and even. So here it's even. So we check, do we have any evens? Yes, we do. How many? We have 1. So that means from any location where this is even to here is a valid subarray. So now we add 1 to the result because this array does have an even number of A's. Then we keep going. Then we have an odd. Oh, and by the way, so for these two, we should have marked them as we've seen it, right? So we've seen an odd number twice. So odd number twice. So here, we're odd again, and we see, okay, have we seen odd? Yes, we have. How many times have we seen it? We've seen it twice. That means we have 2 more here. Because from any previous odd state to this one is even as well, right? Like this is even. And also, actually, let me see. So let's see, odd, even. Oh, I think I screwed this up a little bit. So this needs to be, no, actually, this is fine. Yeah. So yeah, so the other one that's the other one that works. So it is this one is even, and then there's also this one that's even. That's what it is. So these two, right? In both of these, it's even, and that's these two. Not these two, but like these two. And so essentially, the number means like everything after it, because when you do like a prefix sum, it's going to be like this minus this means the area between these two, not including that one. So hopefully that makes sense. But yeah, so here's 2 more right here, right? So even though we have odd here, we have 2 even subarrays. Okay, so let's keep going. So here, and then we need to mark odd. So we mark it after we do the addition. So here we have 3. And then here we have odd again. So we've seen it 3 times. So that means we can make 3 more here. And if you look, this is 1, 2, and what am I missing? Definitely missing something. So this is 1. Oh, right, we're missing this one. Okay. So yeah, so there's 3 there. And then we mark it over here. So now we've seen odd 4 times. And so you can basically just keep going here. So this is odd again. So I've seen odd 4 times, so I can make 4 subarrays. So this would be 1, right, with no A's, that's even. So we can draw it down here. This is 1, 2, 3, and then just the C itself is also even. Right, so that's 4. And so you kind of get the picture. You can just keep doing this. So basically, to sum it up, when we are on an A, check for the count of that state that we've seen, and that's how many subarrays we can add. Because anytime we've seen the state before, any array between those states is going to be an even number of A's, right? If they're both odd, that means, you know, to go from one odd to another odd, you have to add an even amount. And if they're both even, to go from one even to another even, you have to add an even amount. And so from this to any other one, so like here's a pair, it's easier to see it, I guess, instead of looking at the arrays, just look at like the matches. So like this is a match, this is a match, this is a match, this is a match. And so for any one of these, like if I actually had a number of A's here, the number of A's I added would have to be 0, right? Because I went from an odd to an odd. And so that's the main like thing of this problem. But now how do we, like, this is only for one letter. How do we do this for multiple letters? And so the way to do this for multiple letters, basically, there's a couple ways. But the easiest is a bit mask. And the reason you can use a bit mask is because we only have 10 letters. So basically, you're trying to represent for every letter is the count odd or even. So if you use an array, let's say, you'd have to have an array of 10 elements like this, and then each number would represent a letter. So maybe this would be A, B, C, D, E, F, G, and so on. And then you'd have to represent like 1's odd, you know, 0's even, and you'd have a bunch of 1's and 0's. And then you would, to update one of these is pretty easy, right? Like let's say I get to a D, so D would be like A, B, C, D. It was odd now, or it was even, and now I saw a D, so I'm going to update to odd. If it was odd, I'll update to even. And then basically I have to say like, okay, well, how many times have I seen this state before? But in this format, it's kind of hard to use, right? Like in most languages, you can't use an array as a key if you use a key, or like an index in an array or something. But what you can use is you can use a bit mask. Because every single one of these things is only 1 or 0, and there's not that many, this is where a bit mask is good. So a bit mask is good when you have usually 32 or less like values that you need to keep track of. And each value is 0 or 1, which is the case here. So we can just use a bit mask, and a bit mask will basically be, instead of storing an array, we'll store a bit mask. So instead of storing an array, this will be a number. So like this number will be 1, 0, 1, 0, 1, 0, 1, 0, and so on. And so it'll first start as all zeros, right? We'll just start with 0. And then let's say we, let's actually write down the letters here to make it easier as well. So it's like A, B, I think actually in my code, I'm going to have it this way. Yeah, so this will be a number. So these indices actually are a little deceptive. So let's just get rid of all those. And let's just store like the letter it represents. So we have like A, B, C, D, E, F, G, H, I, J. And this is like our number. And it's a 32-bit number, so you'll have a bunch more zeros over here and so on. So let's say we reach let's get rid of this now. Now I showed like why I use a bit mask. So let's say we reach like an F. What we need to do is we need to figure out like what's the number for F. and our base number is going to be a. So what we want is if we want like a to be 0, and then f would be like 1, 2, 3, 4, 5. And the way you could do that in your, depending on the language, you can just get the ASCII value of your letter minus the ASCII value of a. So once we do this, if we reach f will be 5. Then the way to change this mask is you simply do 1 shifted left your letter number of times, so let's call this like f 5 times, or the mask. And basically what that's going to do is, so you're going to start with a 1 over here, and then shifted left your number of times, so it just means you move it left like 1, 2, 3, 4, 5. Because basically what happens here is your number starts off like this, and then every time you shift the 1 left, you basically, what happens is your 1 will go like 1 bit to the left. So like if it gets shifted once, it'll go over here. If it gets shifted twice, it'll go over here 3 times, 4 times, and so on. So if the 1 gets shifted left 5 times, you'll basically have a 1 over here. Wait, 1, 2, 3, actually over here. So, and then the rest of the number will be zeros. So it'll be like all zeros. And when you have that ORed with your current mask, all that's going to do, actually, sorry, you don't want to OR it. You don't want to OR it. I screwed that up. You don't want to OR it. You want to XOR it. And we talked about XOR yesterday. So basically when you XOR a 1 with a digit, it flips the digit. So if I XOR 1 with 0, I get 1. If I XOR 1 with 1, I get 0. So it's essentially, if you can think of all these things as like a light switch, and it will basically flip that switch. So if I have an f that's 0, and I XOR it with a 1 here, this f will now turn into a 1. And because the rest of the number is 0, when you XOR a number with 0, it just leaves it all the same. So you're essentially saying, go to the bit that I need to switch that from odd to even, from even to odd, leave the rest the same. So that's how we can do that. That's how we can like update our mask as we get to a new letter. And then once we update our mask, then we kind of do the same thing. Have we seen it before? If yes, we just do result plus count of our mask, right? Because if we have seen this mask before, that means we've seen this exact state before, and everywhere we've seen this exact state, from that state to this state, every single letter is even. Because if I've seen this exact number before, to get to this exact number again, I basically had to have flipped everything, either not at all or an even number of times, right? Like imagine these are all light switches and they're all on and off. And if you reach the same configuration again, it means you had to flip every light switch an even number of times or not at all. Because you can't go from off to off by flipping a light switch 1 time, right? You have to flip it an even number of times. That's kind of the idea. So if we've seen it before, we're going to add it. That's going to take care of, like if everything was only even. But it says one letter can appear, like at most one letter can appear an odd number of times. So we can take care of the case where everything is an even number of times, where every letter appears an even. But how do we take care of the case of one letter appearing an odd number of times? So that one's actually pretty easy as well. So what you do here is you have your current mask, right? Like your current mask for the letter you're on. Well, in order for one letter to appear an odd number of times, basically how do you have something appear, like we had our example, right? When we went from 0 to 0, this gap has to be even. So how do you have odd? So to have an odd gap, you either have to go from a 0 to a 1, right? Same thing with the light switches. Like if your light switch is off and it turns on, then you have to have flipped it an odd number of times. Or you go the other way, right? If it goes from on to off, you also have to flip it an odd number of times. To go from odd to even or even to odd, you'd have to have added an odd number. But you can only add one of those. So all we have to do is go through our digits of our mask and just say like, well, we've seen this, but have we seen maybe like this A was a 1 instead, and now everything else was even, but now this A was a 1 and now it's a 0. That means the number of A's we've seen is odd. So we can just go through every single bit one at a time and only change that one bit and then see, have we seen that before? And if we have seen that before, the number of times we've seen that, we can also add that to our result. So for example, if this is our current mask, but our old mask was there's a bunch of examples here. So let's actually make this a bit smaller so it all fits. Or I could probably just draw it up here. Here we go. So let's say this is our current mask. This is our old. So for example, if you take any one of these and flip it like this, then every letter is the same. That means the count of every letter between these two, right? Like this, from here to here, this subarray, if the count of every letter is even and even or odd, that means the array between these two, the count of every letter is even, but the one with the difference, the count of that letter is odd. And so that's going to be the one odd letter. So you can essentially just do this for every letter. So you'd say, like, let's start with A. Let's make A the opposite of what it was. Do I have this? Yes or no? And then how many? Then flip this. Do I have that? Yes or no? Flip this. Do I have that? And so on and so on and so on. And the way to do that, it's kind of similar to this XOR thing that I showed before. You just take your mask. And basically what you want to do is you want to flip one bit. So you just loop 10 times. And you do the kind of the same thing. So you do 1 shifted left, I times, right? And you're going to do it from 0 to 9. Because this will be like 0, 1, 2, 3, 4, and so on. XOR with your mask. And then it's the same kind of thing. You take your mask, you put a 1 in some location, and then you XOR this whole thing. And when you XOR the whole thing, like I said, XOR just flips the current bit you're at. So it'll flip the bit to this. And so that's kind of the basic thing. We're going to use a bit mask to store the configuration of our letters instead of an array. You could probably use like a tuple. I guess in Python, you could use like a 10 number tuple and check for that, because you can use a tuple as a key, but a bit mask is just like one integer, so it takes up a lot of space. And then we're going to update our bit mask as we go. And then for every single letter, we're going to check what are the 10 different bit masks we can make with one integer being off, and have we seen that before? And we're going to keep adding all those to the result. So hopefully that makes sense. If you haven't used a bit mask before, it's kind of confusing, but it's not that bad. Like, it's basically just storing an array of booleans in a number, essentially. You can think about it that way. Okay, so let's take a look at the code. And the other thing is, I noticed in Java, arrays are a lot more performant than hash maps. So if you actually code this up with a hash map, it's like significantly slower. So try to stick with like array solutions, at least in LeetCode. I'm pretty sure though in actual like Java, it's more performant as well in general, because there's like more overhead for hash maps. So essentially, what we're gonna do is, instead of storing a hash map of like what's the key of this mask, we're actually gonna just make an array that's gonna be the length of all possible masks. So if you think about it, all possible masks, so there's 10 digits, and each digit can be 0 or 1. So it's basically 2 to the 10th. So you're going to have 1 to 1023 is going to be your maximum thing, right? Because imagine these are all 1s. If these are all turned on, that number, the way to calculate this is it's the same as all of these being zeros. 2, 3, 4, 5. All of these being zeros. And then this being a 1 minus 1. It's the same exact thing. And so this is 2 to the 10th minus 1, but we're also including the actual 0. So it's going to be, 1024. Or not 1024, 2 to the 10th, which is 1024, I think. So yeah, so that's why like the length of this whole thing is 2 to the 10th. So we're going to make an array instead of a hash map of length 2 to the 10th. So we can say int array counts. And this is just basically going to be the size of every single bit mask possible that we can make. And so this will be new int array, and then this will be integer of 2 to the 10th. Because you have 10 different numbers. New int array. Okay. And the reason you have to convert this is because mathpal in Java gives you a double, so you have to make it an integer. So we'll have a result. We need to make it a long, otherwise we get an overflow. So we'll do a result. And then I think that's... Oh yeah, we also need like our current mask, so we can say int mask. We'll start at 0. Then we're going to go through the word. And you can make this like more performant if you want to, but I'm going to stop there. It's already kind of confusing, and this will be like decent runtime. So so basically we're going to loop through every character in the word, so we can say int I equals 0 is less than word length. And like I said, we're going to take the character we run into, convert it into where the one needs to go, and then XOR it with our mask. So the one where the one needs to go is just the character that we have in Java minus a. So if you do like f minus a in Java, you'll get 5 here if you convert that to an integer. This is language dependent. In another language, you can't do this. So like, it just depends on your language. So yeah, so we can say int like, or we don't even need an int. We can just do this in place. So we can say mask XOR equals like I showed yesterday. So this is going to be 1 shifted left by integer. So this will be integer, and then the actual value is the letter. So word caret I minus a. So that will give you like the difference of that character and a, and you'll get a 0 to 9 here. So this is like our new mask counting this letter. Now we can add this to the result. So we can say result plus equals counts of this mask if we've seen it before. If not, it'll just be 0. Then we have to do the loop where we have to try to change every single digit of this mask to alternate and see if we've seen that before. So we could say for int j equals 0, j is less than 10. And then, so we can make a new mask, or we can just make the mask in place. I guess we'll make a new mask. So we'll say int new mask equals, so this is our old mask, XOR with 1 shifted left, j times. Yeah. Because basically, like, we want to try here, 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 just one. We want to flip only 1 bit. So we flip 1 bit and then get a new mask. And then if we've seen that before, then we add that to our result. Because if we've seen that before, this new mask is a 1 character difference from our current mask, which means everything is even except that 1 character is odd. So we'll say result plus equals counts new mask. And that's also the nice thing about not using a hash map here is like if these don't exist, they'll just be 0. So you don't have to do like, is it in there, getter default, all these things. An array is like, yeah, an array in Java is generally preferred. Also, the syntax for hash maps is kind of clunky in Java compared to dictionaries in Python. I think dictionaries are just like more optimized or something, if I had to guess. So yeah. And also because arrays are static in Java, like the fastest way to do stuff generally with an array is make an array of fixed size, because you never have to like resize it. Because if you make a dynamic array and you have to keep growing it, what ends up happening under the hood is like whenever you reach your max length, you like double it or something like that. So here, because we already made it big enough, like this is going to be the best thing you can do in terms of performance typically. Yeah, so this should be it, I think. Oh, so and then the last thing is we have to actually update the count over mask. And the reason is like our mask can't make a pair with itself. That's why we don't update it right away, right? Like for our old example, like if we've seen a state before, like if we're at some state and we've seen the state before, we can make these pairs that are a valid subarray, but you can't make a pair with yourself, right? That's why you don't update the count until you're done with the rest. So you're at some state, you see like, okay, how many have I seen before? I can make a pair with all those, but I can't make a pair with myself. So then after I update this, so if this was like 3, I'd update it to 4, and then when I see this again, now I can make a pair with this state with everything else. So that's what we need to do in the end. So we need to say counts mask plus plus. And yeah, there's like a little bit more stuff you can use to make it more performant, but I think it's going to get really confusing, so I'd rather just not do that. So let's return the result. Okay, let's take a look. Okay, we got something wrong, so let's see if these test cases pass first of all. Okay, they do not, so let's see what we did wrong. So this part should be fine. Oh, I see what we did. So we did calculate a new mask, like we did calculate a new mask, but well, actually, no, yeah, we did calculate a new mask, and if we have seen the new mask before, then that should be fine actually. Yeah, so we don't have to check like if it exists or something, because that should already be handled for us. So that's not the issue. Let's see. Result plus equals counts mask is fine. Oh, yeah, I forgot. Okay. So the thing we screwed up is, remember I said that we have to actually say the count of 0 is 1 because, like, let's say everything is even here. Then you're going to want to return 1 because that basically represents the full array, right? So for all these, like, prefix sums, it's kind of like a prefix sum, you want to say that the count of 0 is 1 because if the whole thing is even, you're going to want to have seen even before to or not if the whole thing's, well, actually, yeah, if the whole thing is even, if the count of every letter is 0 and you haven't seen that before, then you're going to want to like a really easy example is like AA. If you don't have this count of if you don't have the mask 0 equals 1, then when you have this the count of A is 0, right? And you're going to want to have seen that before to account for that case. So that's why. So that's what we're missing. So we need to say counts 0 equals 1. And that should handle it. Yeah. And yeah, as you can see the runtime, so it's a little bit slower than these, but it's like 1 millisecond away. They're all roughly the same thing. So yeah. And so this is going to be so essentially what we're doing is we're walking through our string, which is O of n. And then for every single, like this is O of 1. Is it O of 1? So I mean it's roughly O of 1 because you're basically doing to do a XOR, you're going to have a mask of 10 characters, so it's like, yeah, O of 1. And then this is 10, so this is O of 1 as well. So I'd say, like, if this is just O of n, and space is O of... So here we're storing the number of total bit masks possible, and the number of total bit masks possible is basically 10, or 2 to the 10, because it's the number of characters. So if you wanted to get, like, technical, it would be, like, number of unique characters or something. So, like, characters, or like this. 2 to the characters, and because you only have 10 characters, it's 2 to the 10. That's how many, like, different things you can store. So this will be 2 to the 10th. Yeah. Okay, and yeah, that's going to be all for this one. Hopefully it wasn't too confusing. If you haven't seen bitmasks or any of this stuff before, definitely a little bit more confusing. If you do feel like this is super overwhelming, I'll link some, like, prefix sum problems that are just, like, an easier way of doing this problem with just, like, normal numbers that you can try first. And it's basically the exact same idea once you recognize that is that. And yeah, in the future. And then so other things you can apply bitmasks to, it's pretty common to apply them to dynamic programming. So you're going to have some things like, I have, like, 10 keys I can pick up, and I need to represent, like, how many I've picked up, and the actual, like, which key I have matters. So things like that are good for bitmasks, and some other things like that. Basically, I need to have a small number of items, right, up to like 20 or 30, and every item has a state of true or false. That's where you want to use a bitmask. So it's like a Boolean array of 20 to 30 or 10 to 30 items where you don't want to store an array, you can just store it in a number. That's the basic use for it. So hopefully this was helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.